So we're going to learn from history, and really the purpose of this talk is to introduce you to you, or maybe refresh your memory of a very simple technique of dealing with time series. It's maybe a little bit underrated, or I don't see it that often uh, publicized. Usually people, when you say time series, they jump straight to recurrent neural networks. And it's nice to be able to apply them because recurrent neural networks are sequential, but you don't have to use RNN. If you use this technique, you can use RNN if you want to, but you can also use linear regression or random forest. Okay, so I hope this will be a useful time for you, and so I'll just keep going. So a little bit about me. So I teach these courses on the right-hand side at ISS. I used to be at Microsoft in the United States. So I moved here about 2+ years ago. I'm gonna hide this control again. 2+ years ago, and I've been teaching mostly machine learning and a little bit of IoT, mostly in the intelligent IoT area where we do edge computing. We basically putting machine learning algorithms onto small devices so that they can evaluate in real time. So I have a few links here. So my bio, if you want to read more, my LinkedIn and my GitHub. Okay, most of the time I update the GitHub. So yeah, because it's most, yeah. So if you want to keep track of me, you can just look at my GitHub rather than my LinkedIn. So today's topic, we're going to look at definitions of time series, how to apply time series data, how to prepare it, train, and any next steps. Okay. So time series definition, I pasted a Wikipedia, kind of sort of long-winded, a bit hard to digest definition. So I'll just break it down a little bit. It's a series of data points. Okay, so we have a series, a sequence listed in time order. So the data points are not in random order. Okay. And the hold on a second. So the sequence of data points are usually successively equal space. So I'll talk about that a bit more in the next slide. But just remember that the points are not in, basically in regular intervals. So this means regular intervals. Okay. And then it's a sequence of discrete time data. So the word discrete here is confusing. It doesn't mean that the data is discrete. The data can be continuous, like your weather forecast, your temperature is a continuous number, right? It's some decimal point. Or if I take my temperature twice a day, like I'm required, I get, today is 37.2, right? Not, it has a point number there. Okay, so it's discrete is modifies the time. So basically, it's not continuous time, but it's every so few intervals. Okay, and a shortcut I like to keep mentally is if you can plot the data with time as an x-axis, right? Time as x-axis, then basically it could be an indication that it's a time series. Okay, so keep that in mind when you think about time series. Okay. So here's an equally spaced time sequential signal. In fact, this is the one we're going to use in the demo today, the walkthrough. I basically went to data.gov, which is a government website with a lot of public data collected from all the different, sensors and all the different data sources around Singapore. So data.gov.sg, if you haven't seen it before, because some of you are new to this, so I would just go briefly show this. Okay. So this is a website, data.gov.sg, Singapore's public data. Singapore is not unique in this. So a lot of government agencies, especially in recent few, maybe 5-10 years, have started putting data online. Because they have all this data, they don't know what to do with it. So they put it online. Hopefully someone knows what to do with it. Okay. So we've got a lot of different categories. A lot of these are time series data because that's the most common. Okay, so here's the one that I chose for today. It's on the front page. It's the GDP year-on-year growth rate. Okay, so it's a percentage. That means it's not the actual GDP. It's just the growth on over the previous year. So some will dip. We'll look more into this. So this is where I got the data. Okay, So let's go back to my slides. Okay. So we go back to this. So it's a time sequential signal. So if you look at the data, it's hard to see on the graph, but if you look at the right-hand side, like this is a table. Uh, this website provides both the graph and the table. Okay, so if you can actually inspect the data, you see that it's actually in quarters, 2020 Q1, 2019 Q4, and so on. Okay, maybe a bit hard to see, but just know that it's time space, time sequential. Okay, so and basically we have quite a few latecomers. Okay, we have the data that is you can plot on the graph, and the x-axis is time. Okay, so that's a key characteristic. So if you don't want to look too deeply into the data, you suspect it's time series, look for a plot that has time on the x-axis. Okay, so other examples, very common, stock prices. One of the most popular, I think every time I teach machine learning, introductory machine learning, there's bound to be one project that tries to predict stock price. Okay, so stock prices is a very popular one. Weather data, like today's temperature, humidity, sales revenues, and measurements of sensor data. Okay, so the middle column you can ignore. It's just telling what it is, but time series is really this column value percent and this column quarter. Okay, so without you need both. You need this column, the quarter column, the time column, to order these things in time. Okay, that's how we can plot this graph. Okay, so a time series can be periodic, so it doesn't have to. It can have a pattern. So a very basic time series is a sine wave. So if you remember from maybe school, we plot sine waves. Cosine waves also similar. It's like a wave over time, right? Where time can be the x value. So this is a periodic time series. Okay, if the x-axis is time. So a more real world example is same website, different data set, relative humidity over the past maybe since 1980s all the way to recently. So you can see that it sort of has ups and downs. Okay, maybe every few years we feel like it, maybe some ocean currents or something like that. It has some interesting little little bumps. Okay, so it doesn't have to be very evenly spaced. It can have some, sort of vague cyclical seasonal things. Another good example of seasonal is shopping habits. So during, for example, purchase habits on e-retailers during Christmas holiday season versus, off season, right? Okay, so that's one characteristic of it. So a common question that I get from about time series is, so if I have a list of dates in my data set, okay, is it a time series? An example is things like customer invoices. So I have an invoice. Basically, let's say I'm a retailer, and I send out invoices. I have a whole, Excel spreadsheet of invoices. I have the ship date. I have the purchase date. So all these are dates, right? They are also time. So question is this a time series just because I have dates? Okay. My answer is it depends. Okay. It depends on what you're trying to do with this data. But generally, what you look for is, again, can I plot this in a graph? And can I put the date in the x-axis, and can I have a graph that makes sense? Okay, the graph has to be some kind of signal or sequence of the data point. So in this case, it may not make sense because maybe the invoices are not related. They are different items. So I can't really plot a graph, or on this date, I have this amount, but it's a different item, right? So the relationship between these two, for example, the first row and the second row might be completely different, okay? If they are all the same item, for example, if they are all, I don't know, these days we all buy food online, right? So let's say every week you buy something from NTUC, it's the same thing you keep buying, maybe it's toilet paper. So yeah, you can have the time series of toilet paper, prices or how much you spend on it over time. It's the same data point, right? It's the same signal, really. Okay, so that can be a potential time series, right? So that's one thing you can do. Another little tidbit is even if you cannot treat this as a time series, you can still use the dates. So for example, it may be interesting, the month may be interesting, the year may be interesting. You can actually take the dates and do some extraction of the month, the year, the date, right? And maybe that can become a column, extra column that tells you, okay, this is during off season, or this is during, you know, uh, very holiday season, right? So you can still extract certain things out of it, but it is not a time series. Okay, time series means you can have to plot on the x-axis. Right? So another common question, what if I have multiple time series? Okay, so most of the time the simplest case is you have one series, one signal, and that's great, right? In this case, same from data.gov is COE premiums for different categories of cars, okay, vehicles. So I think the lowest one is like the one that nobody buys anything. And then like there's maybe category A, B, C, D. So you can look at these, sorry about the very small font. I couldn't get it to fit otherwise, but this is the size that they gave me. So category A is probably this red color thing. So it's one time series, 2, 3, 4, 5. So there are 5 time series here. It's easier to see here too. Okay, so basically each line, let's say this line with the smallest one. This one is category, I think E probably, even though the color doesn't really match. Okay, so for every data point here is only for category E. So if I go through this, I will have to filter out category E. So the first, I have to take this value, 32500, very small, cannot see, but this value, and then I jump to the next category E value. So it's about the same amount. Okay, it could be category D actually, because D is very small. Yeah, this is D. So this is category D. See, it's always in the 4,000 or very small numbers. Okay, so you can plot them separately. They're separate signals. So the answer is, if you want to use all of them in one machine learning problem, you have to think about whether they are dependent or independent. Okay, basically a shortcut way of thinking about it is, if it's dependent, that means one category can be used to predict another one. Okay, let's say people who bid for category A, certain prices also bid for category B in the same price. Then these two are linked together. So maybe you can use them in one model, as perhaps you can use B's input history to predict A. Okay, but if they are completely independent, like say this category D, completely unrelated, right? Right, this one is going up and down, but this one is like just stable. Then you can't really use, you have to treat this separately. So you can only use the signal alone and maybe add other factors like, I don't know, drop. I think category D is kind of maybe some motorcycles or something like that. So maybe any feature that applies to usage or demand of motorcycles. For example, recently we have all these Grab food and Deliveroo, right? Maybe more demand for these. You can use that to predict the price, but nothing from the others. Okay. So if you have multiple time series, you have to think about, are these series related? Can you use one to predict the other? Is there any, or are they independent? And there's no point. Okay. Okay. How about audio, video, motion, and so on and so forth? So these are also sequential, right? So this is a video signal with each frame, right? Each picture is a frame, right? And then this is motion capture. Let's say in a movie, if you want to capture some for CGI or some action, right? So the person moves and the sensor data will be captured. Or even audio signals, right? Audio signals, when I say something to you, it comes in as a basically a sound wave, and the sound wave has amplitude, right? So if I speak softer, then the amplitude is lower. If I speak louder, then the amplitude is higher. So that's a signal in time. So these usually have some special techniques. So you don't really apply what we will cover today, or more likely what we will cover today is not enough to do this. But the idea of using Windows is still there. But you will have to do some signal processing, for example, for this. Maybe do some convolutional neural networks to extract from images. So some special processing is needed. Okay. So today we are mostly dealing with this kind of signals, like just a number over time. Okay, the most basic one. Okay. So we'll just go into two common applications of the signal. Okay, so let me pause and check if there's any questions. Okay. Okay. Okay, I will get back to those questions later. Okay, yeah. So so we have two common applications of that we'll cover today. There's more. I have a slide that shows you more applications, but we'll just cover these two basic ones. First one is how to predict the next value, and the second one is how to recognize a pattern. Okay, so the left one is also known as regression. So for those who have a little bit of understanding of ML, machine learning, regression predicts the next value, whereas classification recognizes a pattern. Okay? So regression is used in forecasting time series. So given my some time series data over past few years, forecasting helps me predict whether it's going up or down, or say staying the same value. Okay, so this is forecasting. Okay, so we're just trying to predict what the future will be based on history. Okay, so that's one type of problem. Another type of problem is to recognize patterns. So for example, this is GDP year-over-year change, right? So you notice that there's some very basic, some very, very really terrible dips, right? The growth just drops over these few years in the 1980s, and then in the late 1990s, and then in 2008. So those dates may sound familiar to you, right? Because they are the recession dates. So this do align with the different recession slowdown periods. So rather than knowing based on reading the news or anything or having some pre-knowledge, what if you can recognize this pattern just by looking at the signal and training a model to recognize this kind of pattern? Okay, so this is pattern recognition, also known as classification. Okay, so we'll look at these two. So before we do that, one thing that we would, I need to set some basic knowledge here. In order for you to apply ML or deep learning, you have to basically figure out how to formalize a problem like this or this into machine learning terms, right? So you need to figure out how to feed this into your machine learning system. Okay, so a simple way to think about it is think about the system as having input data fed into an algorithm. The algorithm can be a neural network, can be something else, and that outputs a prediction. So the neural network will calculate something, based on our input data. It will spit out a number, or it will spit out a prediction, right? Recession or not, right? And during training, how do we update the algorithm is by comparing it with the real value. We compare the prediction with the real values, right? And then we somehow figure out a way to adapt the neural network or adapt the algorithm so that the prediction will be as close as possible to the truth. Okay, so that's the training phase. So we have to define then what is the input data and what is the target. Okay, before we even go with the algorithm, we need to define the input data and the target, and then figure out how to massage the data and how to compare with the target. Okay, you compare with the target using metrics such as mean square error or accuracy. Okay, so deep learning is a subset of machine learning. So this diagram applies to deep learning as well. It's a general purpose formulation. Okay, so that's what we will be doing. Okay, so how do you formulate this problem? We have to figure out the inputs and we have to figure out the targets. Okay, so the inputs, for example, a very typical time series will be on your T is our time step. Let's say this is in hours, hour 1, hour 2, hour 3, so 4 hours of data. And then X is some signal that I'm trying to predict. Okay, so basically this signal, at every time step, every hour, I have a different reading, right? So this is my raw data, okay, on the left-hand side. Okay, so what we are trying to do here is maybe we're trying to predict what the next value will be. So after hour number 4, let's say we are at the 4th hour, 4 p.m. We want to see 5 p.m. what is the value going to be for X, right? So we will define the X values using a technique called windowing. Okay, so here's a quick cheat sheet on it. So basically, I will create rolling windows of the data, okay, as my input. So the very first value at time t, instead of just looking at one value, I will look at his current value and the next one. So you see that I added another column, which is just the next three values shifted up, right? 20, 35, 88 shifted up, okay? So I will repeat for the second and third. So after a while, I will run out of values, right? And that's okay. We can handle that, okay? So I will define this as my input, okay? So this is basically, if you take away anything from this class, and if you are new to this, this is really how the gist of this whole class, okay? How do we use this technique and apply it to machine learning, okay? Basically, we take windows, right? The window sizes we have to find a way to determine. It may not always be one. It may be maybe 100, right? Maybe we need to look at history further back. We will figure out how to do that. Okay, but this is really the gist of the technique. And then for our target, why I put question mark here because I don't know what it is. Okay, I haven't formulated my what I'm trying to do here yet. I haven't figured out the application or I haven't specified the application. Okay, what I mean is that why will be is different whether you do this, okay, or this. The y is going to be different. Okay, the x may be the same. The window is the same, right? Because it's looking at the same signal, but the y could be different. Okay, so we will have to determine what y is based on the application. Okay, so two things from this slide. The inputs is some kind of history, and the y is application specific. So for example, if I'm trying to predict the GDP for 2021, I think this is 2020, right? Or maybe this year, no need to predict. We know future. Then I would create a window, right? I'll use that as my input, and my target will be the value just right outside the window. Okay, let's say I have 20 values here. This will be the 21st. Okay, of course you can do 21st, 22nd, 23rd, 24th all the way, but the most simple approach is just take one value and say this is the target. Okay, so this window is going to be slide across the whole series. So I will have transformed this sequence into history and target, history and target, history and target, history and target. Okay, and then until finally at this point I have no target because I ran out of windows, right? So I will use my machine learning model to predict what's the target outside the window going to be. Okay, so this is one illustration of a history sample. The window size I will show you how to determine, but just to sort of formulate the problem, we will use windows snapshots of the samples and the target value. Okay, so this is what we're going to use to train. Okay, so this target value used where? Used to compare when we train, right? We have a prediction. The prediction can be garbage. It can be very good, perfect, but we need to compare it with somebody, the real truth, right? So this target is going to be compared to this to figure out the amount of error so we can update the algorithm. Okay, so this whole process is called machine learning because it's sort of a meta algorithm that updates in a function. Okay, so it does it automatically through a loop, right? And uses this process. Okay, so no human intervention. So similarly for recognition, same sample, okay, but now the target is not the value right outside. It's not the next value. It's whether or not this is recession. For example, if I'm trying to predict recession, right? Remember these circles are what I'm trying to detect, right? So in this case here, maybe I say this is not recession yet because it's not like deep, right? So just remember, I'm looking at the value right. I'm looking at this window and say, is it recession or not? Okay. So because my growth percentage is still above 0, right? I'm still sort of growing in my GDP. Whenever we see GDP growth, the government is very happy, right? And they say, oh, GDP grow. So it's not recession. Okay. But if I slide my window and my window happens to land in this box right here, then I want my recession to be true. Okay, so I will have an example later in the demo. Okay? But the key point is we still slide the same history sample window forward in time. Window size will be determined, but let's say we know what it is. We'll still slide it and we will have target labels, true, false, true, false. So here will be false. Then after I slide it over here, it will say true. Then I slide over here is false, 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 true, true, you know. So you see a bunch of true, false as the targets. Okay. So the gist of pattern recognition is to be able to identify whether or not this pattern exists in a particular snapshot of the data. So we use Windows to look at the snapshot because we can't do the whole thing at once, and we can't do individual. It will be a bit, it will be hard to see. Okay. So which takes me to my next point. Why use a window? Okay, this slide is very busy. So if you look on the top hand, right hand, there's just two reasons. Okay, more than one value is usually needed to determine direction. Okay, what that means is, given only one value, okay, let's say I only give you one value, 2020 Q1, negative 0.7%. Can you tell me, can a human tell me what the next value is going to be? Is it going up or down? Okay, now if you know some external information, like you know that, oh, because it's during COVID times and you know we enter into circuit breaker, so yes, it probably will go even worse. But that data is let's imagine we don't know that. Okay, let's imagine that that data is not available to the machine. So if the machine just looks at this line, he doesn't know it's going up or down. Okay, so so we need multiple values to at least indicate some direction. So if I have the previous years, 2019 Q4 and 2020 Q1, I know this is in a downward trend, right? From 1 to negative 0.7 is a drop. So maybe if things doesn't change, this is going to drop further or at least stay in the same rate. Okay? So you need more than one value, hence a window. Second reason is we need a way to preserve the time sequence ordering of the data. Okay, so we preserve the time seriesness, okay, by forcing the data to be always chronological. Okay, so this point is a little bit tough to show you right now, but just know that I need a way to make sure that my input data is always in sequences from earliest to latest. Okay, later on I'll show you why. Because what happens is we will shuffle the data before we train, right? And if you shuffle it, right, you will lose. If I shuffle this by time, I'm going to lose this jumble up the series. Okay, there is no longer a time series. So I need to somehow ensure that I have a chronological element in my data. Okay, so those are the two main reasons. One is to determine the direction. Second is to make sure it still stays as a time series, no matter what I do it. Okay. Okay, so we just pause for a quick review of the questions. All right, so okay. So yeah, I appreciate if you post all your questions to everyone so that they can see. First question from Gilbert. Will COVID affect models, especially related to GDP and stock price? Absolutely, yes, it will. So what happens is you probably need a feature to indicate whether it's COVID or not, or whether you may also need to train the different model. So you can have a pandemic model versus a non-pandemic model. Okay. Correlation covariance, I didn't mention that at all. So not really talking about that yet. But we will look at autocorrelation later. Okay. Don't know, every 10 years, moving average. Okay. All right. So again, please send any questions to everyone so that it's pretty clear. Okay. So now let's switch gears a little bit. I talked for about 40 minutes already. So let's make your hands move a bit. So you can go to this URL, which I will paste onto the chat window as well. Okay. Okay. So if you go to this URL, let me make it a URL. Maybe this will work. Yes, okay. The second one, the clickable one. So if you click on this, it will take you to a web page where we have, I'll show you, it will take you to this web page. Okay, it will look like something like this after it loads. Okay, so we were going to walk through a Google Colab notebook and just see how the things I talked about are applied. Okay, so okay, so I will show you what it looks like. So if I go to second, so bit.ly, oops, okay. So ISS History 101 goes to the GitHub repo, and sometimes this notebook GitHub may give you an error and cannot load. Okay, if you can't do that, I'll send you the full link later. But if you see this, you can just click on this, open in Colab, and that will launch it in Colab. Okay, so this is the link I'll send to people who cannot load it in GitHub. Oops. Okay, so give me 1 second to share that. Sometimes GitHub's auto rendering of these notebooks is limited by the size of the notebook. Okay, so the second link is the same. Is the click after you click on the button. It's the same thing. Okay, collabresearchgoogle.com is actually where it ends up. We should be in. Okay, finally, after you have redirected a few times. Okay, so you should see a notebook. Okay. And the slides and the notebook, I mean, you have the notebook right now, so you can see it. The slides will be shared with you after this talk. I think maybe a few days after this talk. Okay, so so this is the demo notebook that I'll walk through. I'll walk through it in pieces, so not the whole thing. Okay. So go back to the slides. Basically, what we will do is we will look at loading the time series data set from data.gov. Then I'll pause a bit and look at finding the right window size and go on from there. Okay, so I have a few slides in the middle that I'll jump back and forth. Okay, so let's just dive into it. Okay. Okay, so this is the, so Google Colab, just a quick overview what this is. So this is a kind of a environment, as a web-based environment, okay, using Google's servers to run machine learning and actually to do pretty much anything related to Python, and I think you might even do, I think it's just Python, to run Python code. Most of the time people use it for deep learning or machine learning. Okay, so it's a free service. The catch is that to use this, your notebooks are, first of all, not private. So anyone can see them if they can crawl the URL. Second of all, you access, you have to somehow upload your data on it. Okay, and so it's convenient because you can just use Google's machines. Let's say, see, if I run this, it's actually, if I open the files tab on the left-hand side, so there's a few tabs here on the left-hand side. If you open the files tab, it will connect you to a machine where you can actually see the temporary storage. So there's some sample data here, which we will not use. We will use our own data, okay? So, and you can see that this is actually a machine on Google's cloud. So this is the amount of RAM that's provisioned. You know, looks very generous, but you know, for deep learning, sometimes it's not enough. Okay, this is usually a Linux machine running Google's Linux flavor, maybe it's Ubuntu. But the beauty of it is that it has all the libraries installed. Okay, so what we'll do is we'll look at how to download the data set and how to formulate into a machine learning problem for forecasting. Okay, right? So it has all these libraries already installed. So here, these are all part of Colab. I didn't have to install them separately, and I always have the latest versions. So that is helpful and convenient for me as a data scientist or someone who trains machine learning people. Okay, so but if you are doing it locally, it's possible to download this and run locally. I will not cover it here because of time constraints. I have a requirements.txt in the GitHub repo with all the requirements, all the pip that you can pip install. Okay. Before I start, I think if you are new to machine learning, I think the 40% of you, you will be a little bit lost in this area because we'll look at some of the code, but don't worry. It's, I will try to just do high level and you don't have to type any code. But here's some very handy references. These are cheat sheets for all the different libraries that you can use to look up what we do, okay? Okay, so I'll start. So to run this, you need to log in. So if you click on run cell on here, right? Or you can also do run, just use this button. If you click on this, if you're not logged in, it will prompt you to log in, okay? So because I am logged in right now, you can log in to the Google account and run it, okay? If you prefer not to do that, you can, it's okay, you can just watch, right? You don't have to be forced to participate, okay? But it will be interesting if you know machine learning and you want to play around with it, okay? So I just executed this, oops, that one. I just executed this to import libraries, okay? So these are the libraries I'll import, and I'll go through them as I cover them, okay? So next, we're going to download the data set. So right now, I have no data here, okay? So I'm going to get the GDP data, the URL for downloading the data, okay? So how do I get it? Basically, I'll demo. So if I go to this page, you see there's a download button. So I right click on the download button and I copy the link, okay? Because this, if you just click on this, it will download a zip file. But what I want to do, right? I copy this link, I paste this link here. I want to download the zip file in my environment. So this is a machine that is running somewhere in Google server, okay? So if I just click download here, it's not gonna be, it's only on my local computer, okay? There's many other ways you can upload. You can also upload to it if you don't like this way, or you can mount your Google Drive, okay? So I'm just gonna run this. Basically, it just uses Python to get this URL and then extract the zip file, okay? So if you run this, you see after a while, if I refresh, you see that magically the files has appeared, okay? So this is my data. It's a CSV file containing the dollars and, sorry, the percentage and the dates. And this is just metadata describing the data. Okay? So that's how you can get it. You can also upload if you prefer to. For example, if you click the upload button, I can upload whatever I want, right? And use it. So it's quite useful. Okay. The only thing is this machine is temporary. So if you don't save your data somewhere that's permanent, after 6 hours, this will be recycled, okay? So some people would rather mount their Google Drive, so the data, the machine learning models and all that, will be saved, okay? But these are the things you can learn as you try out Colab, okay? For us, this is a demo, so I don't care. It's okay to wipe it. So I can get the file name, because why? I want to get this file name, right? I'm too lazy to type it, so I want to copy, right? And then I'll paste it to this CSV file here. So I'm just looking the file, getting the file name and actually opening it. So this part is really where we'll start the process, okay? Earlier on, we're just downloading it, okay? Of course, if your data is somewhere else, your process of extracting, getting the data is different from mine. But starting here, pd.read CSV, we're gonna, it should be the same. So if I run this, okay, you will see that this opens the CSV file, okay? Right, I told it to look at the dates, convert them into actual internally pandas dates, so it knows how to do date calculation. And I said, I want the date to be the first column. So the column numbering is based on, starts from 0 lah. So I say index column. So you see how the quarter heading, right, is sort of out of, it's not aligned, okay? This is Pandas way of telling you this is the index, meaning that this is the whole data set, if you think of it as like a database, right? Database has index, right? Like first row, second row, third row. This one just says 1976, first quarter, 1976, second quarter, so it's indexed by date. Okay. Indexes are useful later when we do queries. Okay. So this is like the magic here. Okay. So head is just to show the first 5 rows. So if I don't show the first 5 rows, let's say I don't do head, I deleted this. If I run this, I get the whole thing, but maybe the beginning and the end. So I get the first 5 rows and the last 5 rows. Okay. So it's if you want to see the final data. Okay. So either way is okay. Okay. This is just to inspect the data. So level 1 is this useless column we will not use, but we will use the value and we use the quarter. Okay. So I'll just restore this back. Okay. So this just shows the first 5. Without the head, it will just show the first 5 and the last 5. Okay. So let's do some exploration of the data. Okay. So we're going to plot the data set. It's a general rule of thumb. Usually I encourage you to, after you've loaded the data, to try to find a way to visualize it, because it may not be what you expect. Okay, maybe some missing dates, right? Let's say I loaded the data without plotting it. I cannot tell that maybe some dates here are missing, or maybe it's not the data I want. So it's always nice to visually verify. Okay. So what I do here is I plot the data. I take the value column, okay, and I do a dot plot. Okay, so in pandas, so if you hover over this is also another cool feature of this Google Colab for learning purposes, because who can remember all the different options, right? Maybe sometimes I can, but it's only after doing it many times. So and I don't remember every single parameter, what it is. So you can always hover. So I take my mouse pointer, I hover, and you can see that, oh, this is doing plotting, and there's so many options. I'm only using like the basics. Okay. So this is plotting, setting the figure size to be one size so we can all see, marking every point with the X. See, X, 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 right? And then set the title, set the X label to be year, Y label to percentage change, showing the plot. Okay? So basically, it's just a very basic plot of this guy. 8.2, 7.4, 7.2, right? So you see here, this should be 8.2, 7.4, 7.2, and so on and so forth. So there's many of them over years. So at this point, once you've done this, you should actually go back and check, does this plot match this guy? Because maybe in the process of getting the data to your environment, some of it got corrupted, some of it got lost. So it's always good to double check. So hey, this plot looks like this. So good, I can safely say I got all the data. I didn't miss some. Because sometimes you can get data in multiple CSV files, right? Because one is too small the data set is too big, right? So it's always good to plot. Okay, always if in doubt, always plot. Okay. So I'm plotting this just to say that, oh, okay, this is the data I'm working on. Okay. You notice that the points are connected. That's because plot is trying to draw lines to connect the points, but actually they are discrete. So this is an example of discrete values, right? I said earlier that we have discrete time values. So even though the percentage change is a continuous value, like it's a decimal point, the data points are discrete in the sense that it's discrete in time, right? The data points are discrete in time. So it's only every year you only have 4 points, not 365, not infinite. So it's discrete in time quarter intervals. So nothing much here. I can get some statistics out of it. Did I run this? I didn't run this. Okay. I need to make sure I run every cell because later you get errors. Okay. So if you are following along and you're clicking this, right, just make sure that every single cell you click, because if you miss, sometimes if you forget to click, right, it will, you get an error because it didn't assign, maybe it was running some Python code that didn't get run. Okay. So just make sure you go through and click if you are going through and following it. Okay. So I'm just getting some statistics of how many data points, what is the average value, what are the percentiles, what's the median, maximum value. Okay, it's just to inspect, just get a feel of the data set. I can also do, so here at this point, I will digress and I will look at autocorrelation. Okay, so remember what we said earlier. What are we trying to do here? We're trying to figure out, let's say if we want to predict the next value, right? We need to figure out the window size to use, right? I'm not going to use the whole data set, even though I can. It's not going to be very useful. It's not going to show me too many trends. I'm going to use smaller window sizes, but I need to determine the window size, right? So that's where we are here. We're going to plot a plot that looks like this, okay? So let me go back to the slides, okay? So we are here. Let me go maximize this. So we are here, we are loading the time series data set. We loaded it, now we're going to find the right window size. Why? So that we can find the right thing to use for, we're doing this first, do this, right? So I can say I need a way to calculate what is the appropriate one, okay? So this technique is problem specific, meaning that if you're doing forecasting, you can use this technique called autocorrelation, or you can even use partial autocorrelation. If you want to discount the nearby values, recent values, you can use. So basically, this is like you can treat this like a black box. It's basically a way to figure out how related are values at different time intervals. But if you're doing pattern recognition, then it's really depending on the pattern, okay? So pattern recognition will be, if I'm trying to recognize this pattern, like this giant dip, right? I need to at least get a window that is able to capture this size, right? So maybe 1, 2, 3, 4, 5, maybe about 10 points, right? So I will just look at the data, inspect it, and sort of figure out what the appropriate one is. There's not really a scientific way for pattern recognition. It depends on the pattern. Okay? Whereas for this, you can do autocorrelation because there's a mathematical way to compute whether this value here is going to be correlated, which means it's going to be able to be predictable by values in all the way back here. Okay, so of course we know the value right before it is going to be quite easy, but if I include earlier values, how big can my window go back? How far back can I go? Okay, so this tells me how far back can I go, right? The white window size. So we use autocorrelation. They both still involve some domain knowledge because autocorrelation is not just going to spit out a number and say, use this number, you will always be successful. No, it just gives you a range and then you still have to decide, okay? So autocorrelation basically is how dependent the current value is from historical values. So we want to look for high values. Large values, positive or negative, is good. Means it's very correlated. I think there's an earlier comment in the chat about covariance and correlation. Same idea. So that means if the value, historical value is high and it's highly correlated, then the current value can be predicted from it, right? So high positive correlation versus high negative correlation means that when historical values change, current value will change with it, right? There's some relationship. So large autocorrelation means there is some relationship just by inspecting the whole series. Okay? If it's near zero, means it's noise. Okay? So I have an example from Wikipedia. It's almost noise. It's almost like white noise because you see that the values of X, right? It's just hovering around this noise level. Maybe it jumps up a little bit here, but most of the time it's like almost like white noise. Okay, so this is a noisy signal. You can see that the autocorrelation is actually quite low. So anything below this blue color, between these two blue bands is low. Right, high is here. Right, so it's saying that, oh, the first value of course is high because it's itself, but after that the second value is not very correlated. Maybe you have a few here, but in general it's quite low. Okay, so this is just a measure so that we can figure out what the window size is. The window size will be this, is 0, 20, 40, 60, 80, right? So if I pick a window size of 80, okay, my score is going to be very low. It's not going to be very easy to predict, right? Values that are 80 80 samples in the history, right? I went too far back. I can't predict what the value will be. So for example, if I'm trying to predict this value here, I don't know if you see my mouse pointer at 80, right? I can't really use this value here. I can't really use these values to predict this value here. This is what this is telling me. But if I'm trying to predict this value at 80, I can maybe, just based on this, use the first few values. So I can maybe use this guy, his first history, very nearby history to predict this. I can probably use that. Okay, so we'll see a application of it. Okay, so let's just jump to the application of it. So okay, so here's the autocorrelation plot. Okay, so I run this. What is it doing? It's calling this function plot ACF, which is you hover on it, right? It says plots the autocorrelation function, plots legs on the horizontal and correlation on the vertical axis. Okay, so you pass in whatever x is, which happens to be my value, and I set the axis so I can do some customization. Okay, so the x-axis is called lag. Okay, lag, lag. The y-axis is the autocorrelation. Okay, so how to read this diagram? First of all, earlier I said high is good, right? So high values like this are good. Low values like this one is horrible, terrible. Okay. Second thing, look at the band, the blue color band. This is default, I think is a 95% confidence band. Okay, so let's see. Does it tell me? Sometimes it tells me. See, so alpha, see this option. If a number is given, the confidence interval will be 95%. Default is 0.05. Okay, so so you can so default is always 0.05. So you can actually tweak the confidence interval as well. Okay, so basically this tells me how to read this diagram is when I feed in the whole sequence. So this thing is the whole sequence, right? Not just the first few values, not just the first 3 or 4. The whole thing, it goes in and it computes for every value. It computes the autocorrelation by sliding a window of different lag. So it went and slide window of lag 1. For every value, compute it with its previous one. Then now it tries window of lag 2. For every value, compute the correlation with 2 values in the past. This one is 3 values in the past, 4, 5, 6, 7, all the way. Okay. So this is on the whole series. And what this tells me is, if I want a fairly good autocorrelation based on just the sample, 95% interval of the whole data sample, the data set, I should use a window size of no at most 0, 1, 2, 3, at most 3. Okay, so remember this starts with 0. 0 is always 1. Okay, because I am always related to myself. Okay, so you can always ignore this 1 and look at 2, 3, 4. So I can use window size of 1, window size of 2, 3. If I do 4, I'm not going to have a very good outcome. Okay. Later you can try, if you have time after this session, you can try different window sizes to see if it actually correlates with what matches, aligns with your understanding. So here I'm just going to pick window size 3 because I want enough data so I can predict the future, right? I don't want to just use one value. Maybe it's a little bit too much, but I want to see if I can account for more history, right? So that's why I said window size is 3, largest number of lags. Okay? Okay. So just to reiterate, this technique it only works if I am doing forecasting. If I'm doing pattern recognition, I need to use another way, okay? Which I have as an example in the next section. Okay, so I'll move on. So windowing. So now we've determined the window size should be 3. Okay. So what that means is what that means is if I go back to my problem formulation, this guy, right? I've determined that the size of this guy, the width, is 3. Okay. So right now I'm drawing it more than 3 but it should be smaller. Okay. So I need to make this window small, and then I can slide this window all across and get my targets. Okay. So that's what I'm doing. Okay, So since I have a logical stopping point, I'm going to look at the chat to see if anything comes up. Give me a sec. Calculation, yes, the correlation is calculated based on, I think it's done based on convolution. So you can actually look at the documentation and see, yeah, convolution is a common way to, not convolution neural network, but the convolution operation, which is shifting in time domain. No, the window cannot be calculated automatically. However, not in this means. However, what a lot of, you probably heard of auto ML, automatic ML. I'm sure there's somebody who thought of the bright idea of integrating this into auto ML and just picking all possible window and then training one model for each and then giving you the highest one. So it can be brute forced, but not in this manner. Okay, good questions. So yeah, the trend right now is for companies like Google, Microsoft to offer like sort of one-click solutions. Data Robot is another good example. They sell solutions where you just use their dashboard, right? And then they will train all kinds of models and just give you the best ones. You don't even have to think. And those, they will have some way of configuring autocorrelation if you are using forecasting. Yeah. Of course, with Python, you can build it yourself also lah, but yeah, we're not covering that. So here, so let's show you just the mechanics of windowing. I'm not going to spend too much time on pandas because it will scare people, but I'll just show you the outcome. Okay, so apologize if I'll speed through this part. So you just know that there's a way to do the windows. Okay, this is my original data set. Okay, right? I'm just looking at the value column. So you see the column is not there, but it's actually there. This is the values. The column title is not there. So I'm going to use this thing called shift. Okay. And it's a common, it's one of the easiest ways I know to do, create a window, okay? So I will just shift the data set up by one step, okay? So meaning that, see I am at 8.2 is the first value. I will shift it so that 7.4 is now the first value, 8.2 will go away. So my first value will be 7.4, okay? So I will shift it up and now it becomes this, okay? Okay, so if I continue on, okay, and you see now, the last value is NAN because I have no, the last value is gone. 0.7 is the last value, right? And after that, I got nothing. So it just says there's a placeholder, nothing, okay? Don't worry too much about that. Then if I shift by 2, you notice that 7.4 now is gone, right? Now I have 2 nothings. So I have a way of creating columns where I'm just shifted in forward in time. Okay? See, the column is shifted forward in time. You can ignore this thing. This quarter thing is very confusing. Just ignore. I just look at this. It's shifted forward in time, right? Okay. So how we do this? We're going to take these 3 columns and then we're going to concatenate them like that. Okay. So pandas magic. I won't spend too much time on this. This really requires a pandas course. Actually, the introductory Python course that we have does talk about this, but you can also look it up online. So basically, I'm just taking this output of these 3 shifts and just concatenating them and adding them as new columns. So my original is this first row, t plus 0. I've renamed the columns also, so it's clearer. And then the second one is t plus 1, starts from here, right? You see this? 7.4, now shift up, 7.2, okay? So so it's a bit like circulant matrices, if you know linear algebra. So basically the shifting up, except we don't do the bottom. Okay. So what I'm seeing here is I'm actually creating a new features. Okay. So these are new features. I originally had 1 series. Now I have 3 other series, which are just offsets of this series by different time steps. Okay. This is offset by 1, offset by 2, offset by 3. Then you see at the bottom triangle, it is the triangle is starting to grow, right? Because if I offset by 3, I have means there's 3 missing values. Okay, I will get rid of those. So I'm going to drop these 3. Okay, not doing anything with them right now, but I'll use what I have here. So this is my window data set. Okay, this is equivalent to this guy. Okay, okay. So if I do that, let me make sure I run this. Okay. So I cleaned it up. I drop the NA. Drop NA will delete any rows with NA. So this is my final input. Okay. All right. So this is what we have. This is the window data set. So what do we have now? We don't have target, right? We only have the X. Actually, we do have the target. What I mean is that I can define this as the target. T plus 3 can be my target because it's just right outside. If I say, so in machine learning, you really get to define the problem however way you want, okay? Because I know that based on autocorrelation plot, right, that window of 3 is the biggest window I can get, right? That's still outside, higher than this 95%. So higher confidence than 95%. Here are lower confidence. I should use the third value as my target. Okay? So what I would do is I would take T012 as my input. Okay? So this is exactly what I'm doing here. Okay? T0. So I say Y. So it a little bit of convention. In machine learning, usually we call Y as the target. X, capital X is the input. So capital X, because it's usually a matrix, right? And if you look at this, you can see that X dot shape, which is just the number of rows, number of columns, is a matrix, right? It's a 174 by 3 matrix, 2D array, and Y is 174. So the number of rows, number of data points I have is 174. Okay? So that's my data set. I have defined my data set to do this, sorry, not this one. Yeah, to do this, exactly this, history sample target value. Okay, so I have basically did this. This is the shifting thing. Then I set my Y to be the third column. Okay, so I'll pause here a sec and address questions because the next one will be the neural network, exciting stuff. Okay. So the question is, use a live data feed in come with a result? Not really. Basically, you can't really, you can compute autocorrelation, but it will not tell you the window size to use. Okay, autocorrelation is just, you can run it, you can get a data feed and run this. There's a ACF, besides a plot ACF, there's other functions to compute the ACF number. So you can still get the, you still get the correlation. You still have to figure out what the fixed window size should be. I mean, you have to define a window size. It's not going to tell you what the window size is. So I'm not sure if I answered your question, actually. You can, so the question from Damien is, why not use one for window size since it's the highest? It depends on your scenario, okay? It depends on your scenario. So it depends on your application. In here, I defined that I wanted to predict, based on the last 3 quarters or last 2 quarters. So the window size is domain specific. Autocorrelation just gives you the possibilities. You can still select, okay? One is not possible. One, you know why? Is itself. So in order for you to use one, you need to know the answer already. So you can't use one. You can only use at most 2, 3, 2 and above. Okay? So because you can't, if you use one, that means there's nothing to predict from. Okay? The plot ACF function is from sets models. Yeah. Yeah, so window size, yes, you can say window size 0. Yeah, you can use this window size too. Yeah. Yeah, 0 cannot be used, but 1 can be used. Okay. We'll talk about overfitting later. Okay. Any other questions? Yeah. So if your scenario, let's say your scenario, right, your application, you have been asked to predict based on yesterday's stock price, closing price, today's closing price, then you can, by all means, use a window size of 1. But if your problem that you've been assigned, maybe by your customer, is he only had stock prices from last week, then you are restricted, right? So you can't use window size of 1, you don't have the data. So you have to use a higher window size, for example, or you have to find some way Or if you know based on your domain knowledge that actually is better to consider multiple days of trends, right? And consider them rather than one day. So it's really a judgment call. The number autocorrelation just spits out what it sees based on the data. You can think of it as sort of your, very dumb machine assistant. It just tells you whether, this is the value, this is the value, but you still have to decide. Okay? There's no right or wrong answer. Okay? It's true that, yeah, I could have set window size to 1 and continued there. Oops. So if you want, you can actually try that later. You can try different window size and see what happens. If you change this, hopefully it should work. Okay, so hopefully I didn't write the code badly. Okay, so let's see one more. Let's have one more question and we'll move on. Yeah, so you can update the, I'm not sure what transition matrix is. So you will have to, if you have the window size defined, then you just use that window size. Yeah. Okay, let's move on. Time series is a very interesting problem. Okay, so one more question. So based on the plot, if we use window size to 3 less accurate, it could be, possibly, yeah, possibly less accurate. Yeah. So you may not always pick the highest accurate based on the data. It may be you are constrained by the demands of what you're trying to build. Yeah. Okay, so but yeah, very good questions. So let's move on. So we have the input already. So we're going to train a model using this. Okay, so we'll look at a neural network. So we're going to use TensorFlow Keras to create a neural network and then do the training. Okay, so this diagram is also in the slides. So basically, let me just go back to the slides so make sure I covered them. Yes, I have some precursor here. Okay, so what we'll do, okay, not right now, we computer autocorrelation, figure out the window size. We're gonna do a simple neural network using just creating an MLP, train it and check for overfitting, okay, and then we're gonna get predictions. Okay? So the neural network is the most simple one I can think of is a 2-layer multi-layer perceptron. If you are new to machine learning, this is probably a bit too deep right now, but I just wanted to give an idea of how it looks like internally. Okay, so if you look on the left-hand side diagram, you will see a bunch of circles, and then you see a layer in like another bunch of blue color circles and a green color circle. So the yellow ones or orange ones are just inputs. So let's say I'm feeding t minus 0, minus 1, minus t plus 0, plus 1, plus 2. Okay, so I have 3 inputs, right? So let me go to my, oops. Here, I have 3 inputs, right? So my inputs, I chose these 3, right? My output is this. So my neural network will take in 3, output 1. Okay, so it will take in 3 and it will output 1. Here, it will take in 3 and it will output 1. Okay, so keep that in mind when you look at the architecture. Okay, so we switch back to the slides. So, so X is going to come in here. Okay, 3 values at a time for each row. So this is a window, right? My window goes in. And what happens to my window? For every value, he's going to be fed into one of these blue color things. These blue color things are known as neurons. Okay, internally they look like this. Okay, so what is a neuron supposed to do? Well, it takes in input. Okay, so each neuron is connected to each input. Let's see this H0 here. He's connected to X0 by this line. He's connected to X1 by this line and connected to X2 by this line. So everyone has 3 connections coming in. Okay, there's about 16 of these. How I determine that 16, I will let you know. But just for now, we just say there's 16 of these. I can choose any number, but it's just how this is designed. Okay, so I fed in 1 inputs and weights. Okay, sorry, I fed in the inputs. Now the weights, there are 3 of them, 0, 1, 2. Where do they come from? They are actually assigned to each of the connections. Okay, so there's 3 connections to H0, right? So each one has a weight associated with it. So you can think of weights as coefficients or just some values you use to adjust how important or less important each one is. Okay, so the formula is a dot product of the input and the weights. Okay, right? Which is a dot product is just basically this times this plus x1 times this plus x1 times this. Okay, okay, so it's just we're just doing a product, dot product, and then we're going to add the bias. Okay, so most of the time there's actually another weight, special weight called the bias, which is helpful to push up the overall output up and down just vertically. Okay, so now it's already going a little bit too deep for those who are new to this area, but just think of it, it's a mathematical equation, taking in some input, some coefficient, add some value. Okay, so that's what's happening here. In addition, there is another function that we call activation that we will just convert the output, which is a linear equation, into a non-linear equation. Okay? So why we do that? Because this is trying to model a biological neuron. So in terms of systems in the world, a lot of things happening that we're trying to model functions are actually non-linear in the sense that it's maybe exponential or maybe logarithmic or maybe just flattened. It's a curve. Most of the time it operates on curves. So in order for this neural network to be sufficiently flexible, okay, it's for flexibility, to be able to meet make sure that the output is going to match the target, we usually incorporate some nonlinearity into it. Okay, it's optional, but it helps to get to the solution. Okay, so each of these blue circles is each one looks similar, H2 looks similar. It's just the weight, right? The weight sign is different. Like here, H15 has a 15. So each one has three possible weights. The input is the same, but the weights will change, the bias will change. Okay? So all this is just preamble for the structure of the neural network is just training a bunch of numbers called parameters. Okay. Right? And adjusting them so that our final output has as low an error as possible. So our input is fixed already. We cannot change it. It's our data. We're not changing the GDP. It is what it is. But we can change the W's and the B's. Okay. So when we change the W's and the B's, we can somehow make this output kind of match what it should be. Okay. And similarly, the second layer, H0 to Y0, is just 16 to 1. So there's only one input. So this one has one value. So there's 16 of these going into Y, and he's just going to do a linear combination of this and then output another. So Y0 looks similar to this also, but the number of inputs is 16 and the number of weights is 16. Okay. So that's the structure of it. This is the most basic possible neural network you can build. There's other advanced ones. You can add multiple layers too. Instead of one, you can do multiple. Okay, so let's switch to this. Okay, I will pause for questions after I've done the structure of the neural network. Okay, so this is what we have here. Okay, so how to do? All right, so basically we usually use TensorFlow. TensorFlow has 2 APIs. TensorFlow has 2 sort of interfaces or 2 programming interfaces. One is the TensorFlow that we've all heard before that is very hard to use, very difficult, a lot of code to write. One is called TensorFlow Keras. Okay? TensorFlow Keras basically is a simpler sort of, if you can call it simple, it's a simpler way to use TensorFlow where you just call a few lines of code and it's more user-friendly. Okay? So what we will do, basically we will define a model, which is a sequential model, which is just a sequence of 2 layers, first and second. Okay, so if you're not sure what that means, you can hover and it says just a linear stack of layers. Basically, that's 2 layers, There's now question is there non-sequential? Yes, there's non-sequential as well, but the simplest one is just a stack. Okay. So the first layer is a dense layer, which is the same as the picture I drew up there. Okay. When I say dense, it creates a thing like this. Internally, it will have all these connections. It will have bias. Okay. It will do this. It will know to do this. This multiply plus bias. Okay. So this is all implemented here. I did 16, which is the number here. Okay. That's H0 to H15. There's 16 of them. Input shape is still 3. Okay. 3 inputs. Okay. Activation is the nonlinear function. There's many choices. Okay. ReLU is very common because it's fast convergence and it's popular. Okay, fast convergence meaning you can get the result faster. Okay, get the errors to drop faster. Then after that, I end with one more layer, which is this guy. Okay, and it just has one output. So when you look at a neural network, there's two things that is always fixed. Okay, number one, input shape. Your input shape is not going to change. You only have 3 columns. Okay, it's fixed. Okay, if you decide to add another column later, a minus column, you have to create another neural network, different input shape. Second thing, output size, always fixed, right? Right now, it only outputs one value. You can have multiple values. It's possible, right? You can say I want to output t plus 3, t plus 4, t plus 5, also can, but right now it's fixed. Okay, so these two things are fixed: the output shape and input shape. Everything else, the dense layer, how many internal connections, how many layers here, I can add another one. Right? How many of these? Those are up to you. Okay. Generally, I wouldn't go with. So, for example, I have freedom to do this. I can add another 16. Also can. Okay. Now I have multiple. Right. Now I add 3 dense layers. Okay. The index just changes as I run it again and again. Doesn't mean anything. Okay. So I can do that too. This is all up to me. I can even make this 32. Okay. If I want. Right. But the beginning and end, the input shape and output shape always is the same. Okay, there's more parameters. So one way of thinking about this is you really don't want to pile in too many complications. This is much more complex than this. Okay, this will have another 32 of these, then another 32 times 16 plus 32 connections. Right, this is way too complicated for a simple model. So usually what I do is I start with multiples of basically powers of 2, 16. I could have done 8 if I want to. That's even simpler, right? So powers of 2 will allow vectorization if there's any. It'll be a little bit faster to pack in memory and all that. But don't worry, if you choose something like 13, it's also okay, right? Those things are really don't matter so much at the end of the day, because we are still treating this neural network as some kind of black box function. Okay, they don't really matter so much in terms of which is better understandable or less. Okay, so a very common question I get is, how do you design number of layers? How do you design the number of inputs, number of hidden layers? There's a lot of rules of thumb out in the world. Some people swear by a certain configuration. Some people don't. It really, as long as it's not hugely larger than 3. I have 3 inputs only. I don't want to do like 124. That's really too much, right? I just some same order of magnitude of this, right? That will be fine. Okay. So yeah, so that's the neural network. Okay. So and then the number of parameters, right? How to compute that is a little bit of detail here. I won't go into that level of detail. If you're interested, you can read the slides later, or maybe we ask when we close. Okay. So we're gonna train the neural network. Okay. So I'm gonna split the test, the training set into test and train. Why? Because I need to check for overfitting. Okay. So we had covered this. Okay. Then the second thing is we need to do how to check for overfitting. So to do that, I need to split the data set so that I can have one that is I can check for whether it's only getting good predictions from the training data. Okay, so I can compare. So that's why I'm splitting the data set. Okay. Okay. Neural networks is very, very susceptible to overfitting because you can easily make a neural network so complicated, too complicated than it should be. Okay. So if I see that I'm overfitting, what I would do is I would reduce the number of, let's say the number of layers progressively, maybe to 8, and then go up from there again. Okay. So that's what I would do here. Okay. So I've split this 25, 75. So what happens is I had 174. Now it's 130 and 44, right? So my training set is only 130. Test set is 44. You can adjust this. So if you choose to you want your neural network to train with more data, to see more data, then you increase the percentage. So there's options to do that in train test split. Okay, so you can look at the documentation for that. Okay, so right. So let me pause for questions. Just a couple questions so that we will keep time. A second. Okay. Yeah, there's still some discussion of the window size. Yeah, definitely you can tune. Yeah. So there's a lot of sort of empirical practices, and that certainly be generous, and you can share here, and it's really good that there's yes, there's discussions here. So yeah, this is good. This is good. Yeah. Okay. So you can't really do a hyper tune if you do. So Ellen had a question about hyper tuning. Yeah, if you install something called, I think there's a hyperparameter tuning model libraries for TensorFlow and for Keras. Yeah, you can certainly put that there. Yeah, yeah. 16 neurons, not 16 layers. Okay, so this is a 2-layer neural network. Okay, we're probably not. There's probably too little time to go into definitions of neural networks, but you can see that this is only 2 layers because there's only 2 sets of weights. Okay, yeah, yeah. So 16, I think I addressed that question. Is really I usually pick multiples of, sorry, not multiples, powers of 2 to the power or something. Yeah, yeah. So we'll go into the number of layers. It will affect overfitting. Yeah, very good questions. So this is tuning a neural network is usually more art than science. Yeah. Overfitting also can happen if we allocate too much training data. Well, overfitting can happen due to many things. Allocating too much training data probably is one of the lesser concerns. It's when you have a much more complicated neural network or you train too long. Yeah. Actually, if you allocate more training data, it can also perform better with tests if the training data is a good representation of your, you know, external real data. So I think more training data is not really an issue. It's really training too much. Yeah, very good, very good. Okay, so some of these questions are probably too deep for beginners. So I think I will probably just continue so you can at least get a feel of things. So notice one more thing. I wanted to bring up one point. So when I did train test split, earlier on I said, oh, we need to split the data set and make windows to preserve the time seriousness. Remember I said the word time seriousness. So now if we can see that actually the time seriousness or the time series characteristic is still preserved because I stored it in the rows. Right? I kept it in a row. So it doesn't matter in the columns, right? I have the order already preserved. So it doesn't matter that I've shuffle the rows. It doesn't matter, okay? So it's okay that after I've shuffled, because train test split will do a shuffle, okay? By default, because it wants to randomize, so your neural network will see the data in more fair way, right? So for time series, we are usually very worried about that, right? Because when you shuffle, like you see now my values are all order, right? 2008 come first, and 2012, then 95. So now it's not a time series if I just look at it like that, right? T plus 0 column, it's not a time series, it's like jumbo, it's garbage. But I still have my time seriesness preserved here because I have fixed the order of the columns, and I have said that this column will have the first value, this column will always have the second value, third value. So this is another value of why the windowing technique works so well, because it's safer. Okay? But if I put a caveat here for those who have experience in it, if this bothers you, you can always, by all means, do shuffle equals false, right? It will have some effect on the neural network, but for a very small data set, really probably not a big deal, okay? If you imagine a neural network as a child, like a baby, like you're training it and you're showing it different things, the things it sees the most frequently, like the earlier data, is going to learn more, right? So that's why we try to shuffle to give it more exposure to things. Okay. So anyway, that's just a little point illustration, not super important. Okay. Okay, so yeah, so what matters are each row for the same quarter. So you need to make sure that your X and Y, X chain, first row X chain, right, has to be for the same quarter as the first row of Y chain. Otherwise your answer is wrong, because you're going to use this to check the answer. Okay. So remember earlier on I had that slide here where I had the system, machine learning system, right? So I need to have the right Y value here to compare with this, right? Because my X value and Y value needs to correlate. And I mean, needs to be from the same row. Okay, so that is important. But that's usually ensured by the code already. Okay, so let's move on. Okay, so all this set up for training. Okay, so finally we can train. So so I did put a note there. There's this thing called validation set. You can actually split in multiple ways instead of just 2 ways if you have enough data, so on and so forth. Okay, you can manage your data set so that you can leave some for really the final testing and just some for during training. Okay, so those things, don't worry so much if you doesn't make sense to you, but if you know what validation data is, I just put a note here. So the mechanics of training, I won't go into too much detail, but this is just basically compiling the model and saying, I want to use this to learn. This is how I learn. A very popular optimizer called Adam, because you don't have to tune it so much, it automatically tune. Loss is mean square error, and I will use mean absolute error as a metric. Okay. By the way, there's a very nice link on the beginning of introducing how to train a model in Keras. So in the beginning of this notebook, there's a link here. Yeah, this one is quite good as an introduction. Okay, so if you are lost by now, which is I wouldn't fault you. There's some very good examples that step by step walk through this. Okay, but in the interest of time, I will just show you that we're training. Okay, so I'll just do. First, I initialize the model with all the setting, and then I'll feed it. Number of epochs, again, I just randomly pick 50 so that I can at least train enough. Batch size, it's usually selected based on how many data points I have. So I have about 130. So batch size of 16 will go run through it maybe 8-9 times. So it's good, right? If I have more data, like let's say I have 1,000, then 16 will be a little slow. I look 16 at a time. Okay. So looking at this curve, so every epoch runs through the whole data set. So if I run through, you see the validation loss is starting very high and is decreasing. Good. Actual loss, training loss, also decreasing. Okay. So this is what we want to see. We want to see a steady decrease and a stabilization. Okay. Yeah. So of course, it's hard to see. You can see eyeball it like this, okay? But you can also plot the curve. So I took the output of the training, which is returned when I train, right? And then I plotted it. So you see the learning curve. So the loss is the training loss, and the validation loss tracks quite well until it converges. So there's no overfitting here. Okay? And I can save the model. Okay? So I will finish getting a prediction, save the model, then I address questions. Okay? So I finished training 50 epochs. Of course, 50 may be too long, right? Maybe I overtrain already, which is why I like to have a curve here to see if my validation loss goes up, but my loss is still down. That means if I'm training, getting better and better, but not as good with the uh, the test data set, that means I am overfitting. Okay? So I save the model and I get a prediction. So I feed in the whole data set so that I can just plot everything with each other. So this is the predictions. Right? So Y predictions are basically what the neural network will say based on my input for every value. Then this is just for me to plot. Okay. So I prediction here, and I did a plot. Okay, so the moment of truth is here. So my truth is my blue color thing, which I plotted earlier, right, when we first loaded the data set. And then the predictions are the orange color line. So it's lagged, right? And this is a very common symptom. Okay, a neural network is only really, it's not going to learn so closely, especially for the very huge jumps, because it's based on history. It's almost like a moving average. Okay, and this is true even if you use a more complicated neural network like recurrent neural network. You can't really do much better than that. What you could do is you can maybe use a window size of 1, and that will track much closely, but it will also be noisier. Okay, so this is saying that I'm able to predict, but it's sort of lagging probably by the window size. Okay, but it's still quite interesting that, just by creating a function that looks like, where's this? Just by creating something that looks like this, like just think about it for a second. Like I have some mathematical thing, doing a dot product plus some random numbers that I change the numbers along the way, adding some, passing to another function. I can somehow be able to configure these weights so that I can produce an output like this, right? So it's not something that is that trivial. This is what a neural network is good at. It's good at creating functions to model certain processes. And those functions, you can tweak them, make them as complicated or as simple as possible. But the outcome is it's going to try to get as close as possible to what the truth is. Okay? Of course, in this case, the truth is still quite far out. I can maybe tweak it more. Okay? So a few experimentations, then I'll address questions. As you noted, larger, smaller window size can be tried to see if it affects the result. Larger window size, you should see that it's get even more smoother, so higher error. More or fewer neurons, again, you can add 32, instead of 16. When you get more neurons and more layers, you will start to see probably the error will be lower, but this orange curve will start to go higher, which means it's no good. It's too specific to the input data. It only works well with training data. Okay, so if you deploy the model out in the field, it's not going to work very well unless the data is exactly the same as what you train. Okay, and we can also enhance the training process to stop early, to add TensorBoard, and to automatically save the model. Okay, so these are known as callbacks. So I did a very simple, very, very bare bones neural network and how to train it, but you can always enhance it. Okay. Okay. So let me just pause for questions and we'll go on to the next section. Okay. So metrics and loss are the same. Can be. The links to not sure what links. Yeah, choose the batch size based on, so I'm just looking at the chat. Okay, how to choose a batch size? Yeah, based on number of data points, how fast you want to train. No overfitting, you can see, because there's convergence. The orange line and the blue line are very close. Okay, if the orange line starts to go up, means the loss starts to creep up. That's overfitting. Okay. If it's equivalent to moving average, is there any practical application? Yes. If you're doing more advanced models that take into consideration other columns, not just this data, not just the input data, but let's say I want to, in addition to GDP, I also want to track perhaps the employment rate, or I want to track the US interest rates. So then it's a lot more flexible to have a neural network than just to do moving average and then you try to add the moving average up together. So from a modeling perspective, a neural network is more automatically handles it for you. Yeah. But yeah, I always encourage people who know how to do moving average to use that as your baseline, because at the end of the day, if you cannot do better than moving average, then you're wasting your time. Yeah, so I've had students who do projects and they compare with moving average, and moving average beats every single recurrent neural network model. So, but they can still submit. Okay, very good. Okay. All right, so let's I think we have only about 15 minutes, so I'll just briefly show you the pattern recognition one. It's sort of a bonus, but it's also shorter. Okay, so let me just frame the problem. Okay, okay. So we just only did the first one, but the techniques are very similar. Okay, we did this one, right? We'll try to predict this, and then we have a window size of whatever. Now we try to do this. Okay, the challenging part is finding out how to label. Okay, the challenge, because this one the label very easy, right? It's just the last value or the next few values. This one very difficult because you need to somehow go and set the label in the data set, right? Okay, so I'll fast forward my slides. Okay, we did this, yeah, and then yes. So this is the second scenario where we are trying to do a pattern recognition. See, notice now I'm predicting whether something is true or false. That's pattern recognition, right? This is the pattern. So I reuse the same data set so to show you how it can be approached two ways. I also create a rolling window data set and I'll train another neural network so you can just compare side by side. Okay. So anyway, I think it's easier to just go through here first. Then I'll show you the code because the code can get lost easily. Okay, so what will happen? We just covered this. So we are trying to predict the next GDP value, right? Next quarter. We use the window size determined by autocorrelation, determined by the help of autocorrelation, I should say, but not really. Okay, so I just fix the slides, and later when you get it, you won't get confused. Okay. The help. Okay. Determined by the help of autocorrelation. Okay. Because we had this long discussion of why you not use one, can we automatically determine? Yeah. But yeah, you can get some tools to help you. Okay. So you're not guessing random number. Output is a decimal value, right? Which is GDP. Metrics I use mean square error and mean absolute error. So these are very common metrics for computing how far away is the target from the output. Training loss function, standard is mean square error because it's a very fast to compute. Okay, very nice computationally, works quite well. Of course, we can do regularization and other things, but we're not going there. The task is called regression. So that's what we covered. Okay, so to do pattern recognition, if you could jump to this other side, differences, true or false for target. Okay, in this case, I'm just doing true false, but yes, you can do, if you have multiple patterns like recession, then some other thing, then you have three patterns, but here is true false. History window size, I will show you what I did, is sort of determined by the person. Okay, output probability, okay, in this case, probability true, for true is above 50%, okay, false is below 50%, something like that. Okay, so your output probability. Metrics are called classification accuracy. So how many true is actually true and all that. There's also other metrics like precision recall. We're not going to get there. But the simplest possible one, everyone sort of understands intuitively, is accuracy, right? And then training loss function is binary cross entropy, which is just a type of loss that has a very nice gradient to compute, works for this. Okay, it's sort of similar to log loss. Okay, but that's going into too much detail. Task is called classification. Okay, so you'll see some. We'll look out for these differences in the. I'll highlight them in the notebook. Okay, okay. So then I will. After that, I'll take questions and we'll be done. Okay, so. So first difference, maybe I'll just do the slide side by side. Okay, so I'll just go through this and then I'll highlight the first difference. This is just to plot again because I like to plot. Okay, so let's say we want to recognize a pattern recognition problem require a different target column. Okay, instead of T+3, we need to somehow label the windows as a particular pattern. It's usually a custom process. Remember, you cannot use autocorrelation because autocorrelation is about output of the itself. Okay, we're trying to figure out whether it's a recession. We can't really use the next output to do that. Okay, so but we want to predict dips. So let's say we want to predict these dips. Okay, so I did a custom way to do it, which is I just take the difference. Okay, and I figure out how large the difference is. Okay, So we can see the values that fall significantly tend to represent a dip, right? Like this guy, you know, from here all the way down here, like huge value drop, huge drop. Okay, of course there's ones that go up, but let's say we can figure out the sign of this, which is negative. Okay, so you can approximately do a first derivative, which is just a fancy way of saying a difference. Take the current value minus the previous value, and there's a derivative. Okay. Okay. Now this is specific to this type of pattern. Okay. If I don't want to find, I want to find a different type of pattern. Like maybe I want to find, I don't know, high employment rate or something like that. I can't use that. Okay. I have to do some other way. Okay. Can manually label. You use clustering. So let's say I do a diff of 8. Okay. So this is just arbitrary because I was doing what I was doing is I was just looking at what the value are. So 8 is just how far back do I go in history. Okay. So if I do a diff, which is just to take the value in 8 steps before, okay, 8 steps before. So diff has this periods to shift for calculating difference, or 8 steps forward, I think. Yeah. So it calculates an element with another element in a row. So it's just taking one minus the other. Whichever I take, I just depend, you know, I just choose. So what I did was I played around with this a bit. I looked at the plot. Okay. So I was doing some experimentation. I was doing like 15, right? If I run this, I look at plot like, 15, okay. 15 seems a bit much. I want to try out somehow detect, let's say if I can set a threshold here, right? If I set a threshold here, I want to somehow have this threshold to be false or true for this spots, okay? Right? So let's say I take this thing, I set a threshold. So what I found was, and this is really specific to this process, okay? It's not something that I would say you can use every time. It's really specific to I'm just proving the point that it's really what you define it to be. So let's see this dip, right? Anything above 10 is a recession, right? Recession, recession, recession. Okay, this one not really. This one doesn't work. You see, this one doesn't work because positive GBP, right? But I can go back and fix. Okay, I can go back and fix this. This is a minority. Okay, so I set 8 and I say, oh, okay, it seems like I can just use this way to detect. So I did that. Okay, so this is what I did. I created a plot, another column with recession true false based on this threshold. Okay, so this is completely custom. Okay, completely custom. Not, it's really depend on the domain. Okay, as how I observe the data. It's not scientific. Okay, this is where you would consult maybe econometrics experts, or you know, if you are doing this for economic data, you can ask them for a better formula. Okay, but I'm just a, you know, lecturer, and I don't know any economists, so who still practice. So I just did this. I added a column. Okay, so long story short, I just generated a column based on this orange color thing. If it exceeds a certain, below a certain threshold, I say true. Okay, so da 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 da. Okay, then I plotted it just to see how well it lines up with it. Okay, so what I did was I just took the recession and I just add a red color marker, okay, where it's true. So all these are false, 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 true, 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 true. Okay, good, good, good. Oh, not good, right? This one not good, right? Okay, because this one is not a recession. I mean, at very least, anything that's below 0 should be counted, right? This one may be a borderline, but this one wrong. Okay, so my target label is wrong. So what to do? Okay, I fix. Okay, so I go and fix. So I find everything beyond 2012 here, then I go and fix. Okay, this is just for fun only lah. So these things, I can go and change it. So my point is, don't be too overly reliant on one single automatic process to label. Sometimes labeling things require multiple things like human intervention, inspection, cleaning. It's part of cleaning of the data. Okay? So I went and just set these two to false. Okay? So very long-winded code, but I just say anything that is above 2012, I set to false. Okay, so don't worry too much about this part. It's just appreciate the effect of it. So I just went in and I did my labeling and I cleaned this up. So that's really what I did lah. Okay, okay. Then I trained the model. So now I have a different data set. So where's my data set look like? Let me see. I didn't show you. Let me show you my data set first. Okay. So my data set looks like this. Okay. So this is my new data set. This is a different one from the other one, right? Remember the other one? The other one is called DF window. Let me just compare it for you. Right? For those who are still able to follow me, or window maybe. This is my other one, right? This is my first data set. Looks like this. I try to predict this. Yeah. This is my other data set. Looks like this because I choose a different window size, trying to predict this. So these are two different formulations of the problem, right? Let's clean this up. Okay. I don't need this cell later. Okay, so those are two formulations of the problem. So there's another one, just taking the same data and trying to generate another column. Train the model. Slight differences. Okay, so what is the difference? Very, very slight. Is a sigmoid here. Okay, not what activation did I do? I think I did not know activation. Okay, so that's where I yeah, and I made some slightly different things. So the output is a probability. So I use sigmoid. Right, this is where I use sigmoid. Okay. Okay. Activation. Okay. So that's where the sigmoid comes in. It's just a function to clamp everything between 0 and 1. For those who are, see, hide this first, and I'll come back to it later. Okay, we're almost done. So that's one change. Another change is my history window size is now 8. My target is true and false, right? I use this. Now these two things, classification accuracy and binary cross entropy loss, is here. Okay. Binary cross entropy is here. Classification accuracy is here. Right? So those are the slight tweaks, right? And then the rest is just fitting pattern. Okay. I kept to the same architecture except for the number of inputs, just so we can compare. Okay. So this one actually has a bit of overfitting. Okay. So I train. You see that, how do I see overfitting? You see that my validation loss starts to go up. Or maybe not. Well, okay. Sometimes it will overfit. Sometimes the validation loss will go up. Okay. So this one has a potential of overfitting. Okay. Just by observation. So validation accuracy, wow, quite good, leh. Okay. So that means it's getting 95% correct, right? Actually not quite true. Okay. Because there is imbalance. Okay, so we just show you the plot. So I get the predictions. Okay, plotting it. This one doesn't show you much, so don't worry so much. This one is just saying when I get the recession, predict recession, I do X, the green. Where I have overlap, like this square color, red means it's correct. This one is almost correct. This is wrong. This is wrong. This is wrong. Okay, so I guess I'm correct. Okay, so I'm just plotting it. But what I really want to show you here is the metric, and then I'll take questions. Okay, so this is the accuracy overall, 96%, right? I just take accuracy score, which is just how many correct, how many wrong, right? I compare my Y, which is my actual, and this one is my predictions. Okay, so this is just returning the accuracy, right? So how many of them are the same, how many are different? So it looks quite good, right? Test accuracy also looks quite good, right? 90 something percent. It's the same thing. What's the difference? I just took just only how many? 43 of these. Okay. And then say anything greater than 0.5 is true, right? Otherwise it's false. This one is still quite good. But here's where the problem is. Look at this. Okay. So generally, the number of samples need to be really more or less balanced for the different labels. So for false, I have about 160 samples, and true, I only have about 10. So what that means is when I train my neural network, he doesn't have so many chances to experience what it looks like for this case. So as a result, his he's not as well able to predict these things. So for these scores, the closer to 1 is better. Okay, so like for example, this one is almost perfect, 99. Perfect recall, perfect precision. So these terms are just more about false positives and false negatives for each class. Okay, even the accuracy you can see. Okay, well, accuracy is overall, it's not per class, but you can see that it actually doesn't do so well for the true classes. Okay, for predictive recession, so it gets more incorrect. Okay, as you see the number, it's not one more incorrect. So same thing. If I look at just the test set, okay, test set is about same as a training as a full thing. Okay, so even for the training set, it is not very good for this. So there are some techniques for it, like imbalance learn. You can generate samples. You can generate more recession samples if you want. But that's about it. Okay, so it's a very common problem in classification when you have imbalanced samples. And if you want to, sometimes these occurrences are by design. So recession doesn't happen so often, right? Thankfully. So your data naturally doesn't have that capability to, show the neural network how many recession cases there are. So you have to either accept it or somehow maybe train a separate model, generate different samples to simulate recession, look at other countries. I don't think that will work. So sometimes this is just a fact of life, actually. You're not so good at predicting recession. Okay. So so that's kind of what this is showing. Okay. And we really just only scratch the surface of the of this notebook. And I know I went very fast. But hopefully you get some flavor, at least especially in the problem formulation part, because I spent a bit of time there. This is, again, for those who know machine learning, this is probably one of the most naive ways, but it's very approachable because I've been able to apply it for pretty much any time series data that I have. And sometimes the simpler techniques do work, they work, they're the most reliable sometimes, because you know what to do, what they do. So of course other algorithms can use windowing. You can feed them into random forest and other so what I did was not specific to a neural network. Okay, so the windowing thing doesn't it just how you construct the data. So I can feed into other algorithms just nicely. So you might even try a linear regression model for this, which is the most simplest one you can do. Maybe you want to do a weighted one, a weighted linear regression, because there's so much imbalance in the data. You can also pass this in directly to more complicated. So these are simpler algorithms, are more complicated than the one we have. Now you can also, other than moving average, which is this guy, you can also do other statistical methods. These have some, you still have to tune the windowing. You have to set the parameter or do some auto-tune library to do it. So this is another good one, but this is for mostly for prediction. Okay, and if you are new to this and you want to spend some time on it, I would highly recommend the articles by Jason Brownlee. He goes through step by step in the techniques. He also covers windowing, but he uses a more, I think he uses airline data, and he uses also a more, not as real world as an example. Okay? But it's still very easy. It's still very good to use his code and understand this. Okay? He uses it in Python and NumPy, TensorFlow. More applications of time series, we do clustering with it. Basically, this is an example of hierarchical clustering where you try to take different these are also, again, different patterns and you try to cluster them. This is when you have no labels. You can also do data generation. So this is where instead of just one value, right now, we predict just the next value, right? What if I can predict the next 10 values? Then it becomes more like a data generator. Okay? So those are the common things. Here's where neural network is better because it generally automatically supports multi-value. Okay? But those are more advanced. Okay? So I will take questions now, then we'll do the advertisement. But I think I'm done. So let's see. Yeah, you can get I sent you the link, right? So you can download it. You can download the notebook. So, and you get, so I'll just send a link here again, in case it's buried in all the questions. bit.ly ISS History 101. Okay, so this is a notebook. Basically, that's the one that's in GitHub. Let's see, any other questions? Okay, I'm just going through the questions. I know you cannot see my Zoom window, so I'll try to go far. Using two outputs with one hot encoding, not necessarily. So Alan has a question, one output, two with one hot encoding, not necessarily improve the classification in my experience. It will probably give you the similar results. Yeah, because you know, one will just try to fit. Yeah, it doesn't, because you still have the same imbalance issue. Okay, you have to change for imbalance data, like what I mean is, like here, right? See, there's 16 times more data in one type and the other type. Yeah, you have to address it in the data set. Okay. Dense level can affect the overfitting. Yeah, okay. I think I repeated that question. Okay. Presentation. Okay. Fixed value. Can we set a fixed value to as y less than 0 to determine recession? Yeah, you can. Again, the recession determination is just for fun only. I was trying to prove that you have to do your own labeling or find a label data set for yourself. Yeah. Forecasting is supervised. Classification is also supervised. In both cases, I have the target. Okay, classification and target supervised learning. If you're interested in this, okay, so I guess I have links to my next round of the class. So one more question. Classification model by input 8 previous reading based on itself. Colluding? No, there's no. There are two separate models. So I'm not sure what colluding is. It's autocorrelation. So I'm using the previous value to predict the next value. You can also do a partial autocorrelation. So I have a link of, I think I mentioned partial autocorrelation. If you worry about recent values affecting, polluting the new ones, you can do, let me just go back to my thing. Partial autocorrelation is something you can consider instead of autocorrelation. But that is, I say always try to do the simple thing first. Where is it? Yeah, so there was a question about colluding. Somewhere, yeah, partial autocorrelation is part of the same library. You can do that too. Okay, so one more questions. Okay, good. Okay, so is it possible, last question, is it possible to label one whole series as unlabeled another series? Yeah, you can, but you have to put it back into time ordering, right? So yeah, because you are looking at input time series, so your data has to be coming in. So imagine you are trying to deploy this, your data coming in needs to be in whatever form that it should be, right? So if you create one series for this, just for this, and one series for this, then how do you sort of reconcile it with your input? Because if you come here, if you get your raw data, let's say I get some economic data, I will have to split it up. So that would be hard. But what you could do is you can pass in both so you can create two models, one for predicting true and one for predicting false. You pass to both, and whichever has higher confidence can do it. So you can do it that way. Yeah. So that's sort of similar in spirit to the other suggestion where we have two classes and two outputs, one hot. Okay, so I've come to the end of the what you call it is, let me just get this Zoom thing out of my way. Okay. So the last slide was just if you are interested in learning more, or if if you've done some, if you want a structured way of learning machine learning, with some courses that, okay, so if you like the coding part, if this is something that appeals to you, so if you see the code and you run away, then you probably not enjoy the class so much, because it's more of this me talking and you doing some experimentation. But if this is something that you might be interested in, we have a 4-course series coming up starting in 4th July. You can look into that. Part-time means it's nights and certain nights and Saturday. Okay. Other than that, I have another webinar coming up next 2 weeks. Text processing. There's no neural networks here. It's just how to use Spacey and how to do some topic matching. And then we have a short course in 13 July on RL. So if you're interested in reinforcement learning, which is another branch family of machine learning, for example, how do you train something to play games? How do you train a scheduler? How do you train? Recently there's all these, autonomous driving, right? A lot of these are done using reinforcement learning. Okay, you can kind of get a flavor of that. Okay, so those are the coming ones. And just to part you with this, so machine learning is really, this really resonates with me because you see that what we actually do is those Jupyter notebooks, and there's a lot of misconception. So I hope that this will kind of clear things out, that we're actually doing some data manage, yeah. So what we do is, it's not such a mystery and not so, let's say, it's not like rocket science, but again, it's also it requires a lot of thinking and a lot of decision making at every point.